Hello, everybody. It's Mrs. Pound, and we are starting a new chapter, chapter 6.1 on waves. The first thing we're going to look at are the properties of waves in section 6.1.1. So, our objectives for today's video are to discuss how waves transfer energy, analyze the motion of a medium as each type of wave passes through it, and to compare the three types of mechanical waves. So to get started, what is a wave? A wave is a disturbance that transfers energy through matter or space. And if we look at this drop has produced some waves in matter, and that matter is the water. Now, waves begin in different materials as vibrations. And here, if we were to start a sound wave, we could vibrate one of the strings on this guitar, and you would be able to see those vibrations. They would then make waves in the air that would travel to our ears. Waves are created when a rock is thrown into the middle of a lake. Let's see how that's done. The rock transfers kinetic energy to the water molecules. When the water molecules begin to move and vibrate, they transfer energy to the surrounding water molecules, and a wave is produced. Waves require a medium, and well, not all waves, we'll cover that, but many waves require a medium, and this is any substance through which a wave can travel. Waves can travel through solids, liquids, and gases. An example is sound. Sound can travel through all of those. Um, and you know this because right now, the sound that is going from my mouth to my microphone is traveling through the air, which is gaseous. You've probably been in a swimming pool and you can hear sounds underwater. And you can also hear sounds if you put your ear down on your desk. Now, waves transfer energy, not matter. As I am talking here, it's not that the molecules that start at my vocal cords are traveling to the microphone or that are coming out of your speaker are then traveling to your ear. It is the energy that is passed along. It's not the actual molecules themselves. This is a lot like if you were to do the wave at, say, a stadium or while you're watching a basketball game. If you're sitting on the bleacher, you stand up, but you do not start at one end of the wave and run to the other end of the wave. Okay, so it is just the energy that's transferred, not the matter. Two factors that affect the speed of a wave in a medium are density. It moves faster through a denser medium, fastest in a solid, slowest in a gas. So, a train, you would hear a train through the steel train track if you put your ear to it faster than you will hear it through the air. Also, compressibility. It moves faster in a medium that returns quickly to its original shape. So, faster in steel than in air again. Um, Steel is denser and more compressible than air. Um, Also, think of something soft like a pillow. It's going to move faster in the steel than in the pillow because the steel will move faster back to its shape than a pillow. The speed of sound wave could be increased by transmitting it through a solid or liquid medium or by adding heat to the medium. When we add heat, the molecules and the particles that are making up the medium move a little bit faster. And so, because they're moving a little bit faster, they're able to transmit the energy through them faster to the next particle. Now, different types of waves. The first type we're going to talk about is a transverse wave. This is a wave in which the medium's particles move in a direction that is perpendicular to the direction of the wave's motion. So the wave is moving this way, the particles are moving this way, or I could even do this. Okay? And what I want you to do is next to transverse wave here, draw a snake in the shape of an S because these are always, they kind of are in the shape of an S. They go up and down like hills and valleys. Um, so that will remind us of a transverse wave. And examples are deep ocean waves, some earthquake waves, mechanical rope waves, and x-rays. We're going to shake a rope in class, and you will see that that produces a transverse wave. Now, longitudinal waves, this one you're probably not quite as familiar with. This is a wave in which the movement of the medium's particles is parallel to the direction of the wave's movement. I have a picture of a slinky in the background because what we can do is we can compress the coils on a slinky and then let go, and we see that there's a wave that goes back and forth in that slinky. So some examples are slinky, kind of the way that an inchworm moves, and sound. Sound is a longitudinal wave. Now, in a longitudinal wave, there are what we call compressions and rarefactions. A compression is a section in a longitudinal wave where the particles are tightly packed together. So I want you to label the diagram compression here, where the coils are close together. That is, they are compressed. And a rarefaction is a section in a longitudinal wave where the particles are loosely packed together. So where the coils are farther apart here, label that rarefaction. This is what happens in air. Now, it's not like coils, but in air, the particles become very compressed in some areas and they become spread out in other areas. And that's how the wave is transferred to your ear. There are also surface waves. This is a wave in which the medium's particles move in a circular motion. Some examples are waves on the surface of the ocean, and we're going to talk about this. You will notice if you've ever been on the water that, let's say there's a buoy on the water, you will notice that it kind of goes in a circular motion as it bobs up and down. So some types of waves that can travel through a liquid medium are longitudinal and surface waves. And types of waves that can travel through a solid medium are transverse and longitudinal waves. So our objectives today were to discuss how waves transfer energy, analyze the motion of a medium as each type of wave passes through it, and to compare the three types of mechanical waves. So don't forget your 5 questions, and I will be back with more about waves.